Okay, everybody, so today I just want to talk about a topic that definitely interests me quite a bit, and that's in the area of music, specifically in guitar technology. So today I'm just going to speak about the little guitar machine heads. They're also called tuning pegs, tuning machines, several different names. They're essentially the things that allow us to change the pitch as well as affix the guitar string to the instrument. So just kind of a list of topics I want to talk about today, a little bit of history, where the technology is now, go into systems engineering overview, talk a little bit about the commonality principle and product families, usability, followed up with high-level cost analysis, and a short optimization practice, and then follow and finish it up with some of the axiomatic principles that we discussed in class. So to start, early guitars, as early as the 16th century in Spain, used a similar tuning system to violins and violas used today, which is just simply a peg with a string wrapped around in line. So there's no gears, nothing to facilitate mechanical advantage. It's just simply a string wound around a piece of wood. These days probably use plastic as well. It relies on friction to essentially affix the peg and the tuner to the machine as well as to hold the tune. So you're really relying a lot on mechanical properties here. So more recently, as far back as past 100 years, a couple hundred years, we started using geared tuners. So instead of just relying on friction here, we add a little complex machine of a tuning peg in line with a worm gear, which turns a pinion, which the pinion is attached to the capstan, or the little post that the string is fed through and wraps around. So capstan attaches to the pinion, which attaches to the worm gear, which is driven by the knob. So what this does is it gives us the advantage of having gear ratios dictate how much of the knob turn translates to a capstan turn. So I've seen tuners all the way from 12 to 1 to 18 to 1, meaning that for every turn you have 12 to 18th of a turn of the capstan per degree. So what this does is it allows us to have more robust design, and some of these things I'll go into a little bit more in depth later, but it also allows us to more finely adjust the pitch, so we're not passing the note. With the violin, it's very direct response, so that can cause some problems, but high gear ratios can also make things really slow to turn, so usually don't go above 20. This adds a little bit of manufacturing complexity, but really it's not a crazy complicated machine. It's not a spaceship or anything, so it's not a huge deal. It makes strings easier to install because you're allowing some of that mechanical advantage to take on some of the string tension and be able to not detune as much. So this also just allows us to maintain a more constant tune than just the frictional peg design. And also these things just they kind of look cool. Like this is a bass guitar shown here. It just looks like it's got a very mechanical vibe and very technological. So here we go. So systems engineering, as we discussed in class, is kind of going into design with an end goal in mind, whether or not you have a working prototype. So being able to really break down who it's for, what it's for, and all of that good stuff. So for this design, it's relatively straightforward. Even though the design was pretty revolutionary. So just to break down into some of those foundational questions that we discussed in class, the who is simply guitar players and indirectly the audience that has to listen to the pitch and the tuning and how consistent it stays in tune. The what is the precision tuning system with the geared fine adjustment system that has been introduced. The where, there's not really any specific geographic limits. Guitars are everywhere, and they're made everywhere. More popular in the Western world, but still there's no real limit to that. The why is, as I said before, have more reliable pitch adjustment, better ability to hold pitch, so we're not going to detune as much, and a little bit easier string install. And the how is simply building a compound system relying on gear advantage. So here are the functional requirements of a geared tuner. That first, they are able to change the tune when turned. So that's the whole point of the tuner, is to modify the pitch by string tension. Number two, hold the tune when it is set. So that means when we're not turning, we don't want the pitch changing, simply put. Number three, support the spring tension. So we do not want the capstan post to snap under the tension of the string. Depending on the guitar, the gauge of the string, you can get some pretty high tension, so we definitely don't want it to break. Number 4, consistent pitch modification. When you're relying on friction so much and you're relying on a 1-to-1 gear ratio, you are changing the pitch a lot per turn. And when you're wrapping the string around itself, the diameter is changing. So you can run into the case, it's not a huge deal, but it is noticeable at times. You don't want every turn to be very different than the last turn. So if I'm turning 5 degrees and it changes the pitch 10 cents, you want the next 5 degrees to change the pitch 10 cents, if that makes sense. So a little bit about commonality in product families. So these are 3 tuners by the company Grover, which is one of the more popular third-party guitar tuner manufacturers. The one on the left is probably the highest premium of modern tuners. It's got a locking system, which I'll go into more detail later. But this is, just know that this is kind of like the quote-unquote high end of modern tuners. The one in the middle is also pretty high end. It doesn't have the same locking feature, which is considered a premium, but this is a high end product, probably mid range, I guess you could call it. And then the one on the right is pretty much the most basic. It's a standard tuner, and as you can see, it doesn't look as shiny or standoutish. So what do these all have in common, though, within the product family and that market segment of modern tuners? The housing is relatively similar across all 3, perhaps a little bit different in the super high-end one, but if you look at the one in the middle and on the right, they use pretty much the same housing for the gear train, except there's a different surface finish perhaps, and but that's about it. Different surface finish. One's like kind of a matte, one's a stainless steel-ish, which looks a little bit more quality. But you look at the knobs. The knobs across all 3 are slightly different. The one in the middle being kind of a more standoutish design. It has this cool, edgy, angular factor, which makes it look a little bit more of a boutique design. You'll see a lot of guitars with cool knobs, and that's pretty indicative of generally higher quality because they're willing to put in that extra amount for people who want to invest in that. Besides that, all the latter 2 here use the same 14-to-1 gear ratio, so they probably use the same parts. They leverage the same manufacturing for those things. It's just that the higher end one, the one in the middle, is likely going to just have a cooler form factor and a slight mechanical advantage in that the knob is a larger diameter, so you're not exerting as much force to the part to change the tune. The one on the left has an 18-to-1 gear ratio, so you're getting even more of a fine adjustment per turn of the string. But with the locking mechanism, you're not going to run into the issue of having to turn the knob 18 times to change the capstan because the string usually doesn't wind around on locking systems. And I'll go into detail on that later, but just know there are some differences, but a lot of commonalities here. And this is just a Venn diagram to show some of those things that I just spoke about. Again, the 502 is the locking mechanism, so the premium of the premium. 102 is the basic, and then 109 is within the same series, but is the high end of that. So that one just has essentially a fancier knob and a cooler surface finish. But all of them pretty much share the same outer housing. So there are areas where we can save on cost by leveraging common components. And as you see here, there are some unique things between them. There's some variant things between them, and there's one general thing, and that's the housing and perhaps the capstan design. So these are the 3 main product families across different guitar tuner manufacturers: vintage, modern, classical. As I said before, the last ones I just spoke of were modern because that is a large majority of what is used today, modern guitars. And that's just because they're more robust. There are a lot of technological advantages to the modern design. But vintage guitars still need tuners made because they need to have retrofitted parts to be able to fit into the headstocks. If you have a tuner break, you need to be able to replace it. But you can't necessarily replace them with modern tuners because the hole sizes are different, and you don't want to drill new holes in old guitars because it changes the tonal qualities and can diminish the value. Classical guitars rely on, it looks similar to the violin system, but you see there we actually have the worm gear and the pinion still. So all guitars today use the worm gear system, and that's just because it's undoubtedly better. But it still has that form factor of kind of looking classy with the string round around the string wound around the capstan in line with the headstock form. So here's just a typical looking market attack diagram. So this is just a kind of a thought experiment. If we were to make a product line for guitar tuners across the 3 product families I just spoke of, there is a lot of potential for leveraging horizontally our product components. So for the low end, we could use the same gear ratio. As I said before, with those modern tuners, you could use 14:1 gear ratio, use the same housing for the low end between modern and vintage, use the same gear ratio for all 3, and then save money there. So you adjust some components, but you keep some the same. You could have the same capstan between some of them, you name it. Same knobs even. For mid-range, same deal. We could have a more premium knob. We could have a more premium surface finish. But we could also use the same gear ratio. Let's say 18:1. We're going to make all of the mid-range products use the 18:1 gear ratio. So you make the same product for 3 different lines, essentially. But you just change those things that need to be changed. Vintage guitars usually have a slotted system, so that's what makes them different from the modern system. And the string is attached in a different way that's less robust and usually loses tune differently. Slight different geometry, but that's pretty minutia in the grand scheme of things here. I will say that the one thing I had a hard time finding across a lot of different companies is the vintage high-end series capability. So as I mentioned before, the premium high-end modern tuner uses the locking system, where there's actually a screw that pulls the string down into the capstan that locks it in, so the tune is more consistent and you're less reliant on friction. I haven't seen any of those for vintage tuners, so here's where a business could hypothetically make the decision to look into that untapped potential and make something that's locking for those. Classical guitars generally don't look into that kind of, probably wouldn't look into that kind of thing, just because it's a form factor there that definitely kind of might harm the aesthetic appeal of a classical guitar, and they're not dealing with as high of a string tension a lot of the time. So moving on to usability, the first 2 relatively similar. Equitability and flexibility of the design to cater to a wide range of abilities. There are a lot of really great advances being made in guitar technology to make it more of an accessible instrument to people who have handicaps. Guitar tuners could hypothetically have larger tuning knobs or electrical systems to change the tune for the player. They're not super common right now, but that could also be part of our market attack strategy to cater to those kinds of things. Larger tuning knobs could hypothetically give more mechanical advantage to make it easier to turn the knobs. I mean, obviously, if it's the size of a screw, it's going to be difficult for anyone to do, so we could help there. Intuitiveness, it's pretty intuitive to just turn a knob, so for guitar tuners, it's not a big deal. Perceptibility, you have a direct feedback of hearing the tuning change when you turn the knob, so it's pretty perceptible. Safety, we definitely don't want any sharp edges, so a lot of designs are just rounded and there's no jagged parts. Many guitars have a housing for the gear, as I showed before, but some of them actually have the gears exposed, which could hypothetically cause pinch points. So, for example, if I was making a children's guitar, I would not have an exposed gear train. Usually those are just included because of visual appeal, but if it's little fingers being around them, might want to not include that in a kid's line. Ease of use. Guitar tuners are pretty straightforward. Obviously, make the knob sufficient to turn, and then we don't have any problems there. And dimensionality, we just don't want them to be huge. We want them to be able to effectively turn the instrument without, being like a ridiculous size. So shouldn't be too big of a deal. I haven't seen any that are too crazy out there. So here's just a standard use case. So the most complicated thing you do with tuning machines is change its string. So this depends on which system you're using, but here's just a basic locking system. So you have a guitarist, he's changing the string, he's already taken off the old string. He or she inserts the string into the bridge and then stretches it over to the locking system, pulls the string through the hole, and then tightens down with a certain amount of slack, and then locks that string in, tunes up to the pitch that they want, and they're good to go. So not too complicated, but a large improvement over some of the antiquated guitar systems and even the vintage system. So here's just a high-level cost analysis. Since this is a manufactured part, we do have to look into whether manufacturing the gears ourselves or buying them stock is of interest. Same with the knobs. Knobs could probably be sourced from somewhere. And then just the molding for some of the attachment points in the capstan, probably manufactured in-house. It's not a super involved part. So all of that just goes into labor cost, pretty much. Just have to assemble these parts to make them finished product in the end. And then as far as sales, guitar tuners are sold both to guitar companies to put in their guitars, as well as to be sold as boutique parts. So say you're a vintage guitar collector and you have a tuning head break, some companies will make custom parts for those products. And there are other cases where some companies want to make custom parts for, say, other boutique applications like custom home-built guitars. There's some kind of wacky designs out there for some guitars, so being able to custom make things could be of interest if we make it part of our portfolio. So here's just a high-level thought experiment, just to kind of touch on what we talked about optimization in class. So here's just a little plot I made in Python of a situation where we might want to minimize the weight of both the capstan and the knobs given a few constraints. So dimensionality constraints on the capstan diameter and the knob diameter. The capstan can't be more than 1/4 inch, say, because that would be pretty large itself, but and then the knob can't be more than 2 inches in diameter, which would be relatively large as well, but just kind of for the sake of showing it here. Inequality constraint and an equality constraint. We could have, say here, force balance, and basically being able to say like, well, we can't exert more than this to get a balance of string tension. And then equality constraints, just like we could say, if you're going to have string tension like this, you never want the string to slip, so you want the capstan diameter to be at least this much to ensure that we don't have any problems there. So just kind of a thought. It probably wouldn't get into that much detail, but just want to touch on it. So going into the axiomatic design portion here, we have several things that are going to be our design parameters or design elements that are going to dictate how we affect those functional requirements. So those are the machine profile, so the actual shape, the surface finish, so whether it's lubricated or rough or smooth. Material properties such as what the actual part is made of, and the gear ratio. So here the baseline we're going to use is the violin tuner kind of design, just to show how much of an improvement the gear system is. So here for functional requirement 1, both machine profile and the surface finish affect it just because of that friction that's required to be present. To hold tune with set and not be changing tune all over the place, pretty much every design element is going to be affecting this, and that's just because you have, again, friction is a big component of that, and then the actual shape of your tuner is also going to be affecting that. The string tension is going to be affected by both material properties, being that the capstan needs to be sufficiently strong, as well as the machine profile itself, just because, again, we're going to be really relying on the shape of that capstan and the friction involved to support it. And then consistent pitch modification, again, it's pretty convoluted that the lack of gear ratio and the material properties of the machine profile are going to be impacting that. So moving on to the gear tuner machine to show what that changes, pretty much everything gets improved as far as independence is concerned. The one thing that does change here is that, or does remain decoupled, is the functional requirement 2 is impacted by both surface finish and machine profile, just because in this design you have to wrap the string around the post a bunch of times, and that does change the diameter and then does allow some of that frictional quality to be relied on. If it was perfectly frictionless, the string would just unwrap and come out. So great design. It is decoupled, it is not uncoupled, but it's definitely more robust. So then moving on to the locked tuner machine version. This is an uncoupled design, and that's because the locking mechanism actually removes the need for that frictional quality of the machine profile to be a factor, because you're locking the string down. You no longer actually need, hypothetically, to wrap the string around the capstan. You can just lock it down and change the pitch, and you're good to go. And from what I've seen and experienced on my own personal playing, I've noticed that they stay in tune the best because of this. You're not relying on that friction. So great design, really cool innovation. So yeah, today I just wanted to kind of talk about something that really interests me, and I think that this shows a really great, not crazy complicated application of the things we spoke of in class, all the way from axiomatic design through the commonality principle. There's a lot that's gone into the technology of guitars over the years, and this is probably the most mechanically involved part, not out of necessary complexity, but definitely of application of design principles in order to improve design and make it more usable. So I hope you enjoyed, and have a good break, everybody.